Hiya. So we're going to look at another example of how to look at moments and stuff like that in kind of a real world example. If you're younger, this would be awesome, like a little child. Or if you're like me and you like little toys. So basically, we're trying to get toys from McDonald's. So you know how like McDonald's has those Happy Meals and there's like toys in them sometimes? So say what you're trying to do is you're trying to collect all of the toys, right? Like every child wants every one of the toys, right? And so we're gonna pretend that there's n different coins. I don't know how many they do, so we're just gonna use a random variable, and we're gonna say they all have the same probability of happening. Like there's not one that's more probable or whatever. They're all the chance of getting each toy is independent, so it's uniform in essence for here. And we're gonna purchase a toy at random every so often, right? So the question becomes, how many Happy Meals do we need to buy before we get every single toy? Well, what is this question asking? How many Happy Meals do I need to buy to get every toy? In other words, what's the expected number of Happy Meals I need to get? So that's basically it. I'm asking, what's the expected? So let x be the. So actually, we're gonna tear this down a little by little and kind of figure this out. So we want to know e of x, where x is number Happy Meals to get every toy. Alright, so first let's break this down, right? So the first Happy Meal I get, well, I'm guaranteed to get a new toy, right? Like there's a 100% chance I will get this first toy. So first toy equals first Happy Meal. And the probability of that is 1. So this is just 1. Okay, cool. So the expected value of getting one toy, this implies if n equals 1, the expected value of x is equal to 1. Alright, well, how about 2? What happens if I try to get a second toy now? So every single time I try after that, I have an n over n minus 1, or n minus 1 over n. So second toy, every Happy Meal has n minus 1 over n chance of giving me a new toy. But since every single one is independent and every single one gives me the same chance, that means this is just a geometric distribution. So in other words, if n is equal to 2, well, I need to get the first toy, which is 1 chance. This is the first toy. And then I need the expected value of the second toy. So maybe what it can do is I'll say x of 1 is equal to 1. No, I don't want to do it this way. No, yeah, this is okay. So this will say is equal to e of, yeah, e of x1. Right, so e of x1 plus the expected value of getting the second toy. First toy, this is going to be, so yeah, so let me erase this. This is equal to 1. And the expected value of x2, well, this is just my p with geometric series. In other words, I just do 1 over p, right? So it's n over n minus 1. So that's the chance of getting the second toy. So this we saw, this expected value is from previous things. So here xi is chance of getting ith toy after having gotten I minus first toy, right? So remember, we need to define our variable. So this is where this variable is coming from. So if n is equal to 3, what happens? Well, I want to know e of x plus e of x1 plus e of x2 plus e of x3. So 2 of these we already know. So this is easy. And the question becomes, what's the third toy? So the third toy is basically we do the same thing, right? Every Happy Meal, we've already done 2. We have an n minus 2 over n chance. So again, this is a geometric series with p is equal to, p is equal to n minus 2 over n. So in other words, this is just with geo, right? It's geometric series. So here we get n over n minus 2. And at this point, you should start seeing a pattern. Basically, if we want to do just n, any n, e of x is just the sum of all the e of xi from I is equal to 1 to n. And so this is just, what do we have? Here, this is technically, if you look at it, n over n. So in essence, what I have, n1, n. So I want n, and then I want to subtract. What do I want to subtract? So if I is equal to 1, I want to do 0. If I is equal to 2, I want to do 1. So I want to do I minus 1. And that's basically what I end up getting. So what is this series? Well, let's look at this. This is just n times this sum, 1 over n minus I minus 1. But this we can kind of rewrite, and maybe this makes a little more sense if I write this in a different way, right? If I wrote this as n over n plus n of n minus 1 plus all the way all down to n over 1, and I pull an n in front, well, I have 1 over n plus 1 over n minus 1 plus all the way down to 1 over 1. Flipping this, I have the same series as before. So I can actually just flip this into, this is equal to n times I equals 1 to n, 1 over I. And this, on the term on the right, this is already a series we know, right? Well, not a series we know, but it's something we should be used to, right? This is called the harmonic series. But the thing with the harmonic series is that if we take this to infinity, it is actually divergent. So we can't take this to infinity. But since n is limited, right, we have a set number of n, we can actually calculate this. So notice how, like, above we had n equals 3, n equals 2, n equals 1, etc. So let's try this. Let's say n is equal to 5. Say I have 5 toys. And let's see how many times we have to go in order to get every single toy. So this gives me e of x is equal to n, 5, times 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. Now, if you do this by hand or by calculator, you should get 137 over 12, which is roughly 11.42. So you probably have to go to 11 to 12 times to get all 5 toys. And yeah, so the more toys there are, the harder this kind of goes. And obviously McDonald's is not that nice. Some of the toys are generally less likely to happen than other toys, which means this won't work. But anyway, this is probably a good time to stop. And in the next video, I'll keep going and we'll talk about Poisson distribution, since that's another discrete distribution. And it'll be a good place to kind of go from there. So I will see you then.